Today, we want to solve some trigonometric equations. Solving equations is a thing that we already know about. It's the trigonometric part that we need to put in there. This is why we need to put this trigonometric part in there. Our general thinking for solving equations is to do the same thing to both sides of the equation. Or in more specific terms, do inverse operations in reverse order. Our general plan for solving equations, generally, we solve equations by doing inverse operations in reverse order. Our general plan for solving equations is to do inverse operations in reverse order. This is probably not how it was taught to you, but this is what you were taught. This is doing the same thing to both sides. So if you were taught do the thing to both sides, this is the same as that. We're just being more specific about what to do and when to do it. So I want to clarify a little bit about what I mean by doing inverse operations in reverse order. Inverse operations in reverse order. Start with something that we can solve just by looking at it. If you come across an equation and you're asked to solve the equation, really wonder why. Why is this person asking me to solve this? Be suspicious unless that person is your math teacher, your current active math teacher. When I ask you to solve equations, don't be suspicious. It's my fucking job. If someone just walks up to you and starts asking you to solve equations, that's weird. Walk away, but keep an eye on that person. So we can see that the answer is 3 here, but we want to think about the formal process for doing that. What would you do first in solving this equation? Subtract 5. So you would do this to both sides. You might not write it this way. This is the style I was raised to do. Because 5 minus 5 is 0. And so this side just becomes 2x, and 11 minus 5 is 6. So if 2x plus 5 is 11, then that 2x part must be equal to 6. What would you do next? Divide by 2. I don't know how you write it, but this is how I was programmed to write it. And then I was told to write x equals 3 underneath. And then I lost points because I didn't line up my equal signs. I had a sociopath for a teacher. What can you say? How many of you had this same plan? You don't have to raise your hand. Anybody have a different plan? I'll ask the anti-question. Who had a different plan for solving? Did anybody do these operations in the other order? Did anybody divide by 2 first? So this is what we mean by inverse operations in reverse order. In this case, it was easy to pick out what to do. If we look at what 2x minus 5, x plus 5 does, the first operations, let's think about the order of operations. If we start with an x, the first thing that happens is we multiply by 2. And the second thing that happens is we added 5. And then we ended up at, I spelled end wrong. I was 8 years in undergrad. That's how the x turned into 11. I like to think of this in terms of functions because we're sophisticated pre-calculus trig students. This is how x turned into 11. The function is first multiply by 2, then add 5. That takes an x and makes it into an 11. Our plan for solving is to do inverse operations in reverse order. The first thing y'all chose to do is instead of add 5, subtract 5. Maybe you didn't choose to do it. You were just programmed to do that. But if we do inverse operations in reverse order, then the first thing that we'll do is the inverse of plus 5, which is minus 5. And the second thing that we'll do is instead of multiplying by 2, we would divide by 2. That's inverse operations in reverse order. If we start with bare feet, then put on socks, then put on shoes, we have shoed feet. If we want to invert that process, we first take off the shoes, then take off the socks, and we're back to bare feet. We do inverse operations in reverse order. Any questions? Of course not. It was 2x plus 5 equals 11. We all saw the answer was 3 like 10 minutes ago. A picture is worth 1,000 words. So Leach, draw the picture and shut up. No. 2,000 words for everybody. In general, this is how we think about doing problems. There are some situations like this one where we could change the order. Sometimes we rewrite this equation and then start doing things to both sides. There are certain scenarios where we have to do something else. Sometimes we have add-ons. Sometimes we have to do something else because our operation isn't strictly invertible. Sometimes we have to do something else. There's something else we have to remember because our operation isn't strictly invertible. We have ways to invert it, but it's not technically invertible. And we want to be technically correct, which is, of course, the best kind of correct. An example of this. We know that x squared equals 9 has two solutions, a positive 3 and negative 3. Three squared is 9, negative 3 squared is 9. Remember when we have negative 3 squared, that's different from negative 3 squared. There's just no verbal parentheses. So when we think about squaring something, the inverse would be a square root, but we can't just do that to both sides of the equation. When we undo an even exponent, we produce two solutions. That's an add-on to this inverse operations in reverse order. So what happens here is we can't just do a square root. I spelled exclamation point wrong. Crazy. We can't just square root. We have to know that there are two solutions. That was part of your programming. If you knew that the solutions were plus and minus 3, part of your programming was to know that we can't just do a square root of both sides. So if we had the equation, say x squared minus 5 is equal to 4, we can't just add 5 to both sides and then do a square root. Because when we write square root of 9, we just mean 3. We have to know that even exponents are going to produce two solutions. So that's part of our programming. If we do inverse operations to both sides, even roots produce two solutions. This is extra stuff that we have to know. Now, it doesn't work. We don't have to remember this if we're undoing a radical. So it's only when we do even roots. It's only this even roots part. So for example, if I have the square root of x is equal to 7, to undo a square root, we just square both sides. To undo a 1/2 power, we just square both sides. There are other things that we have to remember. If we can't just go around squaring both sides. But we don't do the plus or minus thing here. That's for when we apply a radical with an even index, when we undo an even root, or when we install an even root. We don't do the plus and minus thing here. We do it over here. If this seems like a lot to remember, yeah, it's a lot to remember. That's one of the consequences of having the way that numbers behave. Questions? Some functions have extra add-ons. We can't just invert. We have to do some extra stuff. In particular, trigonometric functions have this characteristic. Trigonometric functions on their own are not invertible. And at this point, you might feel kind of betrayed because I'm like, oh, first day, we were like all inverse sine. And you're like, oh, dude, you're saying inverse sine all semester. And now you're telling me that the sine isn't invertible? And it's like, oh, well, yeah, that's exactly what I'm saying. Sine, just regular sine of x, That's not an invertible function. We make a sine inverse, but there are a lot of restrictions that come along with it. Any questions? How's everybody okay? Remember, there's an algebra portion of this class too. That's why we got to point this out. On a side note, notice that with this x squared minus 9, we had to remember that there was this plus or minus. And you might be thinking there are other ways to get around this equation. This is a quadratic equation. My training also says set it equal to 0 and solve. That is also a valid thing to do. That's another, but that is another special thing that we have to remember. If the equation is quadratic, instead of doing inverse operations to both sides, we have to do some other thing. So at this point, you might remember that if we have x squared equals 9, one strategy for quadratics is to set equal to 0 and solve. Or sorry, set equal to 0 and factor. Then use the 0 property. But this had to be installed because we can't just do inverse operations to both sides because the square isn't invertible. So we either got to remember our alternate plan of set equal to 0 and factor, or remember that when we do a square root, we got to put in a plus and minus. So here we're using that other alternate method for solving equations. If you see an x squared, one strategy is to set equal to 0, factor, then use the 0 property. Or set equals 0 and use the quadratic formula. Quadratic formula is kind of trash. You could also complete the square. And now everybody hates math. Because like, well, just tell me what I'm supposed to do. It's like, well, you could do this, but if this happens, then it's this. But instead of doing that, you could do this other thing. Any questions? How's everybody okay? Here's what we have to get around. Trigonometric functions have this property. Trigonometric functions are not strictly invertible. Trig functions Sine waves in particular are not strictly invertible. Sine x equals 1/2 has infinitely many solutions. This is known officially as the Pepys problem because when you draw it, it looks like a row of Pepys. Also, I said that because even though it's April 2nd, because this class doesn't meet on Monday. Maybe I should just try to convince you that this is really called the Pepys problem because it makes a bunch of Pepys. And then later on, you could be like, oh yeah, you know, the Pepys problem. And you're like, well, what the fuck are you talking about? Like, well, the Pepys problem. Then I get an angry email from you later. It's like, oh, dude, that's not a real thing. And I'm just in my office laughing. You ever drop by my office? I'm just like randomly laughing. Someone just emailed me because I told them it was a Pepys problem. And they just found out that it wasn't. Any questions? Comments? Snide remarks? How's everybody okay? Take a break. We'll come back and we'll solve some trigonometric equations. We'll learn how to deal with this sine inverse business that apparently I lied to you about. Before we adjourn for the day, I want to talk about the different levels of question that we have on the solving trigonometric equations handouts. There are the first parts. Part A, this is just asking your calculator to remember values for you. So the first part is just asking your calculator about things. When I say this part here, when it's the exact value, that means I'm going to be asking about pi. That's me saying, use pi in your answer. Because when we ask for sine inverse of 0.5, we know that sine of 30 is 0.5. Sine of 30 is a half. We remember that. It's not a quiz, so you can just be like, oh yeah, we totally remember that. And so, but when we use our calculator to find sine inverse of 0.5 in radians, it's like, oh, here's pi over 6 in radians, the decimal approximation of pi over 6 in radians. And so it's not giving us the exact value. So we want to remember that 30 degrees is pi over 6. We don't really want to have to recognize this as pi over 6. We just want to know some stuff. So part A is just how stuff shows up on your calculator. This is what that looks like. Push buttons. That's all. That's what that was about. The second problem was restricting ourselves to an angle in a right triangle. So we're only going to get one. Because there's only one angle that will, one triangle that will fit this description where sine of theta or sine of x is 0.5. Problem C and D work together. This is where we're going to have two solutions. One in quadrant 1, where sine is positive, and one in quadrant 2. Those are the places where sine is positive. And so what we have to recognize here is how we take that pi over 6, how we take sine of pi over 6 as a half and apply that in this scenario. We get our reference angle. And we put that in the two quadrants. So pi over 6 in quadrant 1 is just pi over 6. Pi over 6 in quadrant 2 is 5 pi over 6. In the next problem, in part D, I guess that's the fourth problem, our reference angle is still pi over 6. but we're changing quadrants because sine is negative. Then we bring up the unit circle that we've all got a picture of in our minds, right? Right, right. Just open up the folder where you keep that. Double click on it. My mouse is broken. Just have to remember. That's 7 pi over 6 and 11 pi over 6. The reason that we want to be able to do this is that we want to take that pi over 6 and be able to use it in various scenarios. The same way we want to use the square root of 9 is 3 and make sure that we get both of the solutions, plus and minus 3. We know to use the plus and minus 3. That was a much easier trick than the one that we have to deal with these trigonometric functions. Any questions? Then we escalate even further. And now we're going to take that reference angle, and we're not just going to put it in quadrant 1 and quadrant 2. We're going to put it in every representation of quadrant 1 and every representation of quadrant 2, because we know that these sine waves go on forever in both directions. We don't just want this first cycle from the middle to the middle. We don't just want this one from 0 to 2 pi. We want all of them. And so we have to add multiples of the period. This is just an escalation from the previous problem where it was reference angle in the appropriate quadrants. Reference angle in these 2 quadrants. Now it's reference angle in the 2 quadrants and add multiples of the period. So it's reference angle, quadrants, and then add multiples of the period. So I'll have pi over 6 plus the period a bunch of times. I usually use n. I think this book uses k. Doesn't matter. Use n or k. Those are the appropriate choices. So here we are adding multiples of the period. We go from reference angle plus quadrants, reference angle plus quadrants, plus multiples of the period. That's the escalation. Any questions? So here's what's stressful from a student standpoint. Number one, how am I supposed to remember all this? Secret is you aren't supposed to remember all of it. Like in all this detail. Right now, I'm asking for all this detail. And you're like, oh shit, I am not going to remember all of this. That's okay. What I want us to understand is that there's a way that we have, is that when we're solving this equation, sine x equals 0.5, there's an infinite number of solutions. I want you to first understand there's an infinite number of solutions. And I want you to understand why there's an infinite number of solutions. Because we're looking at this sine wave. We're looking at this sine wave. And if I pick a height on this sine wave, that happens an infinite number of times. Because we just take this, and then we make another copy of it, then we make another copy of it, then we make another copy of it. That's what we want to understand. That there are an infinite number of solutions, why there are an infinite number of solutions, and that we can write down what all those infinitely many solutions will look like. Right now, I'm asking you for all the details about how to write down those solutions. That's less important than understanding that there are multiple solutions to the problem, or infinitely many solutions to the problem. Does that make sense? You see the distinction between those, between what I'm asking you to do? So the extra thing that's messed up about this is I'm asking you these questions coming out of spring break. Dick move on my part, 100%. How's everybody okay? I just need to do, I missed everybody for a week, so I need you to all be really mad at me right now. That's why I come in heavy on the first day after spring break. So, like I always say, it only seems like a lot to remember because it's a lot to remember. But the new thing is, this is a lot of detail that you don't really have to remember. I want you to understand that there are infinitely many solutions. I want you to understand that a trigonometric equation will have two kind of primary ones in that first go around the circle. Reference angle in the quadrants. But also know that there are more. It's like fucking Skywalkers. There's always more. Oh, but wait, there's another. And then Obi-Wan will be like, well, and another one after that too, huh? It's like, well, not yet, not yet. That one's gonna be a Palpatine though. I guess that's a spoiler, but that movie's pretty old at this point, so no, it can't be all spoiler alert for movies that are that old. You know what I mean? Darth Vader's Luke's father. You don't get to have that not spoiled. So that's what we want to think about that. We'll practice this a little bit more on Thursday and then decide what level we're going to be tested on this. It's not going to be a very high level. All right, that's it for today. I will see y'all on Thursday. Everybody have a good day and thanks for playing.